Hey there, Calc folks, back here with another Mathematica Demo video that I want to put together for you. I'm full from dinner. I think I want to try to get these out to you when I can, when I feel inspired for a lot of different reasons here. Just start to unload some of this on you. We're at the end of these topics, and as I kind of pointed out, you know, you first have to walk the path before you can take those shortcuts, folks. And that is kind of what you've been through the last couple of weeks, is you have hopefully walked that path. And if to help you out along the way now, I'm going to show you some shortcuts here using Mathematica, where certainly you can use this to do a bit more advanced work. And if you haven't figured it out, we're going to kind of build on these ideas. These methods that I'm teaching in these demos are going to come back again and again in future demos, and we may rely on some of these to help us get through some of our calculations and just to help us understand this material, folks. I will tell you, I have the second half of the semester already videoed up, so I could really approach things also with a very much a mathematical context, and add to those videos I already have with the Mathematica demos. That is some of the reason I'm behind here, is because I'm not videoed up on all the front half of the semester. So these are end priority here, folks. But nonetheless, something I do want to try to get across this semester. And I think Mathematica, I've learned a lot of math programming languages, or I've learned a lot of programming languages. I've taught myself, if I had to name them, I'd have a difficult time naming them, because I don't really explore them by name. I explore them by when I encounter them, and I encounter them in different games, in different cloud variations. Right back in my days when I learned programming, I learned the programming language Pascal. But I think I've done some C++ programming. I've done some the reverse prefix notation programming, stack-based programming, command-based programming, right? My early days of Go-To back when I was a grade schooler, back in the early 80s, right? That was, a early programming language that I learned. Mathematic-wise, and what was another one when I was a kid? I think it was called Turtle or something like that, if I don't remember correctly, back when I was a child. But no, I enjoy programming, folks, over the years, and so maybe this comes a little bit more naturally to me working in this Mathematica. But I do want to share what I can do here with you and show you what you can probably do also, folks, with just a little bit of time and energy put in, and be able to do something that is going to help you out in your future studies when you go off to university, right? And you're actually studying these ideas. The last thing we want you doing is working on anything by hand, certainly. And if you have a tool like Mathematica in your back pocket, that's a step up. That really is a step up. So let's get into it. We take a look at what we're doing here. I'm already 3-4 minutes into this video, and I haven't even started. Where we're going to go back to is look at unit tangent, and keep in mind we were looking at unit tangent and principal unit normal vectors last time. One thing, just to put an end on that, if we go down to our graph down here, one of the things you'll notice that disappeared compared to our graph up here was that description of forward orientation. All right, we have a graphical issue going on with the arrow. The arrow is a two-dimensional graphical element, where if I want to define it three-dimensionally, I have to define it with a curve. And that is where I believe you've seen me use the Bezier curve. All right, I think we have to do Bezier curve around that T1 inside of that arrow command. Maybe I'm mistaken there. Is it B? What am I missing? Do I need parentheses? No, that's just going to cause errors. All right, well, I'll have to look up how we've done that in the past. Is it a B-spline curve, maybe? Maybe am I just not seeing it with the thickness? Could be any of those different elements there. Ooh, I saw a hint of red in there. So maybe it has to... There we go. Ah, it is there. Folks, it was just hidden with the graphical elements. Notice the G1 has kind of buried it there in the graphics. If we wanted to make sure that graphical element certainly always showed up, you'd have to layer it on top, and they layer from left to right. The leftmost P null is going to be the default options on the plot itself, folks. So now if I run it, it's there. At times though it is hidden, and even though I layer it in there, even it's kind of difficult to see at times. That forward orientation. Changing maybe the thickness of our graphs might help with some of that, right? But nonetheless, we ought to move on. We ought to move on. Now, another thing I was going to show you here, folks, that we might add on here is user-defined, what do we want to say these are? Operations. And let's do an IE on this. For example, what I mean here is a magnitude operation. All right, let's build a magnitude operation here, folks. Let's build an operation, because you've noticed every time we've had to take a magnitude of a function, we've had to spell it out, full simplify the norm of the vector we're looking for, and that full simplify is happening where we're putting limitations on t to be in the real number system. And to spell that out every time can be a bit tedious, where it might be nice to build a user-defined function that just takes as input a vector. And maybe the variable of interest in that vector that we want to define as being real, right? And when we plug input into that, it does our vector, our magnitude calculation. Because where I want to head with this, folks, the next topic we might consider here, we want to look at, let's look at motion, right? Particularly acceleration and the components of acceleration, right? So I'd like to get into that idea here. And that's going to require some magnitudes in the calculation. And we encounter it. You know, depending on your program, you might have to do a lot of magnitude calculations here. And that norm gets a little annoying at times. So let's write this up, folks. Again, maybe we call it the magnitude vector. Now notice there are no functions already named magnitude. And like I said, I want to have it take as input a vector. And I want to have it take as input a variable. Right? And what it is going to do as a function, it is going to run a full simplify, right, on a quantity, and we're simplifying so that we end up having our, be careful there, our variable, right, be an element of the reals, right, where what we are full simplifying is going to be the norm of the vector that we input. Now that is a what we might call a user-defined operation, folks. And it works a lot like a function, folks. In effect, Mathematica is a lot of different types of programming languages built into one. It can be a command-based programming language. It can be a line-based, right? You know, go to the next line, go to the next line, if-then, logical-based programming language, or it could be a function-based programming language. And here we've just written a line of code that's going to take as input a magnitude and the variable of interest and give us back the, it's going to take input a vector and a variable of interest and give us back the magnitude, right? For example, I could say, well, r of t, let's go with that familiar r of t, right? that vector t comma t squared. Right? Certainly we might be interested in finding its magnitude. So now with this user-defined vector, or user-defined operation, I can input the vector r at t, and I can input the variable of interest and hit enter, and it gives me the magnitude calculation for that value. Now, we may be interested in taking that a little further, as we had noted at times. It's nice to have this as a nice simplified result also. So let's go ahead and force the program to simplify. All right. That doesn't necessarily clean this up much, but it certainly is already in a nice simplified form there. We might consider factoring it, right? We could always factor that result. But here, we just made that user-defined function. And now that I've defined it in my Mathematica kernel above, it's there, and I can use it in further programs. Right? You do want to watch the order of things that you put in, and if we were to quit, one of the things we might consider doing here is I have a lot of variables already defined, and we could run into some bugging with defining future variables inside this document. So what I'm going to do is I'm going to go up into my cells, first of all, and just delete all my output. All right? And then under in evaluation, and on the cloud, I'm not quite certain what it is. I think you might find both delete output and quit kernel all in the same place, but I find it under evaluation for quitting the kernel. And you can't see this because the window doesn't show, right? But I've just quit the kernel, so I've kind of erased the memory of my programs in this document. I do want to make sure I put this back in, though. Let me erase my example there, though, before we run it. All right. It says, do you want to evaluate all the cells? No, let's not evaluate them all. Let's just run this one and run any future ones. But the ones above, let's leave unevaluated. And it does ask you that in case you do have any of these user-defined programs ahead of time. And anything above might be useful down below. We could certainly, have this pre-run those programs to call up those user-defined operations, or those programs above that you might find useful down below. But here we're going to start kind of afresh, but I am going to maybe grab this one here and there just to show its use. All right. So I went ahead and ran this one. Notice it doesn't give you much output, folks, because it is set declared. All right. There basically just tells you the norm of the vector if we don't set declare it. And this is one example of when we might want to set declare an item. Because all we've done here, folks, is like I said, we can see its output. Whereas if I set declare this, this doesn't run until this is called upon in our programming, in future programming, as we had seen in our example. So let's go ahead back and set declare that, and set our kernel at that. Right? I am Alt-8ing, so that is why you might notice my text might look different from yours. And when you do Alt-8 in a command cell, when you're, it does make it into the coding cells. It kind of grays it out and kind of treats it as a group of commands. All right? What did I say? We want to look at maybe motion. So here's our classical example, right? The parabolic curve. Right. Again, we might be interested over some bounds from, A to B, right? And again, that might be useful to look at with respect to a plot, right? P1, or let's make our base plot. Again, the parametric plot of R at T over values of T from A to B. Right? That doesn't show much. It's not until I run a show command where I start stacking up these plots that I start to get my plots to form. Right? And what we might do here is make what? Our, what do we want? Let's go up and grab some of the plot commands we had up above. That's sometimes a quick shortcut here. For example, this base plot, let's grab that image size, that labeling, and even that plot range. And we can bring that down into this program. Got my double comma there. Let's get rid of that. Let's add variables g for our range and h in our range, right? And again, let's make our range from 0 to 9, or we could even go less than that, 6. Might zoom us in a little bit, right? So we get a little better looking scaled picture here, folks. All right. If I want to go now a little further, we're going to look at acceleration. So what we might be interested in is preparing up our our velocity vector, right? Our velocity vector is going to be via t, and how do we find our velocity vector? It is the first derivative of our position vector, right? And we might define our acceleration vector, right, to be the, well, we could say it's the first derivative of our velocity vector. That works if we've defined our velocity vector. If we haven't defined our velocity vector, we would note it is the second derivative of our position vector. That describes acceleration. Right? Now, along our curve here, right, we might have a point along that curve. How do we get a point into that curve? Well, we would have to put in a point. Maybe we put in point P1. All right. Let's be careful there. We're going to do a list plot in 2 dimensions. A P1, and what is P1? P1 might be R at, what have we done? C in the past, right? We made that a user-defined value here. So let's look at it at C, and maybe we want to look at the point at 1 in value, right? And that's not going to show up until I come down here and I put in P1 into the show command. And one thing I forgot to do is, if you don't do this right, folks, it's going to put the 1, 2, the coordinate 1, 2, it's not going to align them right, or actually be at 1, 1. It's going to put at 1, 1, and at 2, it's going to put 1. You got to get used to wrapping your points in another set of parentheses. Think of them as a set of points is what we're putting in here. And that's what tables give, set of points. If I wanted to make a whole set of points, I could make a whole table of points here. All right? But we'll leave that off for now. All right? There's just that point in our graph. We can see that there. All right? Now we have defined it at the location of C. If I wanted to change that to the location 2, that certainly can be done. If I want to make the point a little bigger, we might say point size. Oh, wait. We'd have to put that in a plot style. And do point size. 0.002 is usually a good guess. We get a decent looking point in there. All right. Now at that point, we might want to illustrate our velocity and acceleration vectors. And we're going to do that a lot like we had done with my unit tangent vectors. We're going to call out here some more plots, some more parametric plots that are going to be defined as lines. All right. These are going to happen at that defined value as C, where we have this plot occurring. All right. So they're going to start at R of C. We're going to add to them the direction that they're going to move in. For the velocity one, it's going to move in the direction of the velocity vector. All right. Times, right, T. And I got to be careful using T here. I should really maybe say we're going to move in the direction of, let's be careful here, not via T, via C. That's where I was running into error. And then we can use some parameter. I can use T. I might shy away from T. Let's go with N. And this is going to be for values of N from 0 to 1. So it's going to be a full-scale vector. In a sense, N is scaling our vector here. We used this N up above, and we scaled from 0 to 1 with a a vector that was defined as a unit vector. So it automatically made it 1 unit in length. Here we're scaling by 1 the velocity vector, folks. And this is how we define it parametrically. All right. You'll notice if I come down here and I lay that in, right, I do get that illustration of that vector. Now, it's a little hard to see there. If I adjust my C down, maybe I bring that down to 1, right? It becomes a little easier to see. We could even change its style a little bit. Maybe we go plot style. We could go green. Like I said, green I always like. Make it stand out a little differently. Right? We could change its thickness if necessary. But no, that is our unit tangent vector. And it does change length, folks. It does change length and illustrate speed with its length. All right. Here again, we're looking at the what was this? A velocity vector. All right. We could print that here. All right. We can say the print. This is our. Let's make that text. If we don't make that text, folks, it could possibly read any value as a variable and give us the variable output for that variable. And what we notice now, it does tell us the velocity vector. What did we do there? I ran into an error somewhere. Output 110 failed. It's failing on me here. What if we delete all output? Evaluation, quit kernel. Yes, I really want to quit the kernel. Again, I might make use of this, so I want to rerun that program once. And then I do want to make use of this. And it's still failing. Tag integer in is protected. Is it this? If I make that T. No. A, B, C, D, E, T, 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 T. Where are you failing? Failing 24. 22. Set delayed. A, B, C, D, G, H. Let's see. Let's see. T. Well, one thing we can do here, let's see if it's this bug in it. So it was working, wasn't it? When did it get buggy? We get that as N. Man, all of a sudden it's buggy. Let's go quick kernel. So I have a bug somewhere. Where is that Parabola? Let's style green. T. Put that in there. Put that a bit in. I mean, it's still giving us the graph. There's some sort of set delayed bunch we're getting there. But let's print. I'm not going to worry about it right now. That's what you'll run into here is everything will still work fine. But you'll get these little issues that come up. And you can research them if you need to. But everything seems to be working just fine, so I'm not going to worry too much about it. And in fact, you can come down here and go, all right, let's just turn off this message for now. All right. So it was going to give me a confirmation on that. Yeah, let's turn that off. So now when we run it, it doesn't come up, and we're fine. What failed, I don't know. We'll have to look into that too. I think that is this variable. What is it actually R bar double prime here? Let's go with V prime of T. Well, maybe not. Oh well. This is what you'll find. You'll run into this at times, folks. So yeah, that plots on our velocity vector. If we wanted to plot in our acceleration vector, folks, that would be P of 3. Let's call it that. It's going to be a parametric plot. It's going to look a lot like this plot up above. Let's maybe copy and paste that down. Except instead of being in the direction of the velocity vector, it's going to be in the direction of the acceleration vector. All right. And if we come down here and layer that in to our show command, all right. Now why aren't you showing up? There's something wrong with this t value in here. So 0, 2, 0, 2. We're doing it as a vector A of C. R of C. Lead all output. Man, this program is really getting buggy on me. Last time around, I was like, it went so smooth. Sometimes it's spelling. It's not plotting it there either. So I'll play around like this. I don't see it. What is going on here? Do I have it so buggied up? I might. I may have to start this whole video over. We're getting late. I'm getting tired. I'm going to pause this and see if I can't figure this out. All right, folks. I am such a fool that I found the error. Can you see where it's at? Yeah, highlighting it right here. What I had done, this just shows how technical the program is I called that function originally A of T. And this was called down here A of T. Or A of C, right? We were declaring this value as C here. And we were getting an error message. We were saying... -1 of t protected, and I was going, what does this all mean? And I was a little confused until I thought a little harder about it, and I thought, well, notice what we did up here, very second line. Very early on in our program, we declared A. We declared A to be -1, so anytime A was seen in the program, this is quite literal. Mathematica can be, and tricky, and one of the reasons why you might consider how you define your functions along the way in your variable values. It was recognizing that A as -1 in value and then trying to work something with that in the math, and that's why I was getting all these errors, and that's why I wasn't getting the plots that I was looking for down below. So let's change that. Let's make this function ACC for acceleration, and just to add to that, let's make VEL the velocity. All right. VEL, we can get the velocity out of there. I don't want to change anything to position or anything. Let's leave that R bar a T, but we can certainly get more specific here. So there's nothing wrong with then coding this. This is our velocity vector calculation up here. All right. And something we might consider doing also is actually printing in there the velocity vector at t equal to, and then you can actually call up the value c, right, in that print, and that's kind of nice. It says the velocity vector at t equal to 1/2 is, and then what we might follow that with is just our velocity description at c, and it would be 1, 1. Right? We then had the plot of that. A little bit of analysis, plot, and then we had down here the acceleration vector calculation. We might consider doing another print of this, but this time talking about it as the acceleration vector at t equal to c, and doing an ACC at c. I should be all right with the ACC there, folks. I know that's really running the line, but because it's string, because it's character, I think it's going to read it separately, and it does. It hasn't had an issue with it so far. All right, take note. And then we should probably print above this. Acceleration vector. All right, and then we got the acceleration vector at t equal to 1/2. But it does give us that output even though it stays constant in that case. We can turn off this graph. Everything's working fine there now. And actually we can see that if we were to, should turn it off with a proper set declare symbol. And what we do notice now is our plots down below. We get both the velocity vector and our acceleration vector here, folks. Remember this acceleration vector? It's a summary. It's a summary of how much our object is moving in the tangential direction with how much it's moving in the normal direction here, folks. If we wanted to isolate those directions, we know how to do all that, right? We can call up our unit vectors from above if we wanted to. I did get a little fancy here by redefining this formula here, so I might go ahead and rerun that. All right. And we'll come down here and just note this is our base plots. All right. And right now, let's put in some other aspects of this graph. Let's do unit norm. Well, we have the tangent, right? We might need a normal direction. So let's go with the unit normal for now. Right? And while we're at it, we'll get in there the unit tangent. Might as well. We're working on it anyway. So keep in mind where the unit tangent comes from, and let's go ahead and declare that as we did above as a function of t. That's always convenient. Right? And it is r prime of t divided by, and then we wrote that code. And I realize now you can't see this. So let me scroll up high enough so you can see all this. All right. We're going to do the magnitude of vector r prime of t, and we're going to make sure t stays real. That's our variable. Now, it did calculate that in the background. All right, there it is. But it is set declared. If we felt the need, we should be able to make a plot of that into our plot. All right. That is another parametric plot. similar to the ones above, where we're going to plot a line that's going to start at r of c, and we're going to add to it the unit tangent vector at c to full scale. So we'll scale it out by n, right? For n from 0 to 1. Now that's how we have to define it in order to get it to happen parametrically here, folks. We can't quite see it in this graph. Oh, I know why. Number 1. We didn't call it. All right? And it is hidden down in there, folks. It is hidden down in there. What we might do is consider making the velocity vector a little thicker. So to run multiple plot styles, you have to do a directive command. We'll run that as thick. So you can see there the blue on top of the green in our graph. If we were to zoom in a little more, it'd be a little clearer. But that is our unit vector, unit tangent vector there, hidden in that plot. We could do something similar with the unit normal. I'm going to copy and paste this over and show you how quick this can be if you want it to be. All right. We're going to call this the unit normal, principal unit normal. We're going to end up taking the first derivative of the unit tangent, all right, and divide by its magnitude using that little magnitude function we wrote for variable t. And we got to make a new parametric plot here. So we'll make a parametric plot 5, and here we're going to use the unit normal in this. And we want to make sure this plots. Now this one, we shouldn't have a problem seeing it until our acceleration vector lies on top of it. There it is. There's our normal vector. Right? And in fact, to maybe make those two stand out, we might add some color to that. Plot style. Let's go with magenta. Let's add that to this plot style right here. All right. Is it really buried under there? What's going on? Am I going to worry too much about it? Plot style, magenta. I think we're good. I'm not going to worry too much about it. But that's our unit tangent, unit normal vectors, folks. Now, what are we here for? We're here for that summary of acceleration. That is our components of acceleration, folks. And remember where our components of acceleration come from? We have two of them. They are scalar values, and they do depend upon our location for t, right? Based upon our parameter for t. All right? So, we're going to define them. You're going to have the, let's go ACC tangent. That's the acceleration component for tangent. It is going to be based upon location t, so we'll make it a function of t, right? And similarly, we're going to have an acceleration component for the normal, right? And it too is going to be a function of t, right? Remember where the acceleration for the tangent comes from. If you recall, folks, that tangent component of acceleration comes from the dot product of the velocity vector with the acceleration vector. And remember, we got a little bit more specific with those descriptions, right? ACC and VEL given above up here, right? Velocity, acceleration, right? So we can define the acceleration of the tangent at this by taking the dot product of those two vectors, and you can use either the dot command Or another way to do them is you could do dot product by doing velocity of t dot acc of t and use the period as a dot product. That also works, but I like to use the dot command here. It's really quite clear. It stands out there. And remember what we're going to divide that by. That's going to be divided by the magnitude of our velocity vector, right? With respect to variable t here, right? That is our acceleration, our tangent component of acceleration. And remember, our normal component of acceleration is, first of all, going to involve the cross product of these two vectors, velocity and acceleration, right? But not just their cross products. Furthermore, it's going to involve the magnitude of those cross products with respect to variable t. It is the magnitude of the cross products of the velocity and acceleration vector with respect to t divided by the magnitude of the velocity vector with respect to t. Again, this magnitude function, folks, remember that was a user-defined operation up above. I knew I was going to have to use this simplify, full simplify, and normal several times in my calculation here. And I didn't want to have to write this out every time, and I wanted to simplify it where I knew basically it was just going to repeat here with the vector that I put in the variable. And I wrote this so I can change the variable. I don't even have to have the variable change. I could, if I knew I was always going to use t, leave that as t, right? And have that user-defined function in my program here. But I call upon it quite a bit down here in these unit normal and unit tangent calculations and in these components. So that's why I wanted to maybe make use of something like that here in my program. So now this should calculate my acceleration and tangential components of acceleration. It should give them to me as functions if I don't declare these. And remember, these are scalar valued functions. And here, now I got a cross product issue saying the arguments are expected to be vectors of equal length and the number of arguments is expected to be one less than their length. Is it because these are not three-dimensional vectors? Let's explore that cross product for just a moment. Take the cross product of the velocity with the acceleration of t. And missed my bracket here. Vectors of equal length. So I wonder if it is because I'm not using three-dimensional vectors. What if I just put in some three-dimensional vectors there just for the moment? Does it do a cross product fine with those? It does do a cross product fine with those. So what I may need to do here is a slight adjustment. Let me see. It's going to cause a bit of an issue there. This is all just going to be a scalar, so we should probably manipulate things down here. We're going to do a velocity 3D, right? And we're going to go ahead and call out an acceleration 3D. We're going to need that also. These are both going to be functions of t. Right now, this is going to be my quickest solution. Sometimes that is it, or we could do a bit of research here, folks. But I'm going to have to call out three-dimensional vectors where in this system, the z component is going to be 0. Now, the first two components, the first component here is going to come from my velocity function with respect to t, but it's only going to be the first component, and we signify that with a double bracket following the velocity function here. A double bracket surrounding a value of 1. This says I want the velocity function, but I only want its first component. Right? And this will be my velocity function where I'll only, with respect to t, but I'll only want the second component. And then the third component of this will be 0. And then I'll do a similar thing with the acceleration vector. And so we'll be doing this cross product with the 3Ds instead. 3D descriptions. And now we have 0 issue with that calculation. That's what it was, folks, is the cross product was looking for a 3-dimensional value. We probably could have set that up with the 2-dimensional cross product in its calculation. But let's stay maybe a little more true to form. All right, let's call these out. We didn't need to do that for the acceleration because the tangential component of acceleration. What am I doing here? Let's print our tangential component of acceleration, and then we go through all this work, and then this will print the normal component of acceleration. And we might add some sub documentation just to highlight this is where the normal begins. Right? We do have to do that 3-dimensional transformation there, right, of our vector into 3 dimensions. And we call out just the components of our velocity vector, the first and the second in this manner, and this works for any set. You can call out them by a term, right? Using that double bracket there. Now, what we might want to do is put these into our graph. Let's actually use these, right? What does all this tell us? This is tangential component, normal component. These are scalars. These are how much we have to scale, right? Our normal and our tangential unit tangent and our principal unit normal vector by. So we get vectors that when summed together give me my acceleration vector. Right? So let's build those vectors, right, in our descriptions here. And let's put them into the graph. For the tangential here, right? For the tangential, all right, folks, the finish line is in sight. Let's see here. We want to graph these scalar values. We're going to want a scalared. Well, for a moment, let's see here. What do the tangential and normal components tell us? They are scalar values, right? They aren't vector values, they're scalars. Meaning when we multiply them by a vector, they scale that vector, right? They cause that vector either to grow in size or shrink in size. And that is what we're looking at to do with these is we are either going to scale, and you can almost see it in the image already here. This is our normal component, or our normal direction, our unit normal vector. We're going to scale that by the normal component of acceleration, right? It's going to scale that to a certain size. It's going to make it grow out to a certain size to match up with the amount of our acceleration vector that is moving in this normal direction. And the similar is going to happen over here to our tangential vector, our unit tangent vector here. It's going to be scaled to a certain size, right? And maybe we'll draw those out in a certain color here to make sure that we can see them. But we're going to have to make a scaled value of our unit tangent. It is going to be a vector with respect to t, right? And where's that going to come from is our scalar acceleration, our tangential component of acceleration, times, right, our unit tangent vector. All right? And we can actually then, once we define that, we can actually calculate that at our value of c. And that should tell us it down below here. Yep. 1, 1 would be that vector at c. All right. This would be our first of all, scaled unit tangent. All right. Let's just make sure that's coming up as the 1, 1. Oh, what I probably wanted to do instead was actually print that, not document it. All right, the printing will do the documenting. So that is our scaled unit tangent. So that would be up 1 over 1 in this direction. And actually, that probably is the velocity vector here. We're pretty darn close to it in that direction. But if we wanted to actually see it plotted, what plot are we on? We're on plot 6. Right? And I can keep track of that down here in my plot commands, or my show command, folks. All right, I haven't used up through plot 6. Plot 6. And notice this is why I quit the kernel above with the plots above, because there are other plots named 1, 2, 3, and 4 up above. And then there's a lot of other variables named A, B, and C. So I don't want to confuse it with all of that. But we are going to make a parametric plot again. All right. Of now the scaled unit tangent vector. Oh, let's be careful there. At R of C in the direction of the scaled unit tangent vector with respect to C, right? Full scale. So we multiply that by n on a scale from 0 to 1. So that should give us a full scale P6. Oh, and then let's call it out as a different color. Let's plot style it. We got a lot of different plots there. Let's go purple. Purpler. That might work, right? And that doesn't work until we call it down here. And then we should see it there. It is buried underneath that green graph. If we were to make it, let's add a directive here. Not only is it purple, but let's make it dashed. Would we be able to see it if it's dashed? Yeah, we can see it there now if it's dashed. Right, it goes out to a length of about here. Not quite as far as our unit tangent vector. All right. With respect to the unit normal direction, right, we can set up a similar calculation for it. All right. You are going to have your, what we're going to print here is going to be your scaled unit normal, and that actually seems a little, oxymoronic, right? Scaled unit, because it's 1 unit in length, but all right, but we are scaling it. That's kind of the idea here. And then we're going to have a scaled unit normal vector, right? It is going to be a function of t, and we're going to build that by taking our normal component of acceleration, which again is a scalar at t, and multiply it by our unit normal vector at t. Right? And then we are going to do a scaled normal at c and see what our measurement is, right? And it should tell us down below. The scaled unit normal is scaled 1/2. All right, what do we got going on up here? T times the unit norm at t. Is the error in here? No, that's the scaled unit normal. So the error is in here. Did I misspell it? Oh, yeah, I did misspell it. It's, again, the pickiness, folks, the little things you can miss. Scaled unit normal is what I want in there. So I'll set declare that. Scaled unit normal. Here it is. And it should be giving me... Yeah, it is a vector. It is a vector description. And it's not a pretty vector description, folks. We might be able to simplify these quantities. All right. That makes it scaled unit normal a little nicer, and it's scaling. Notice that. And similarly, my goodness, is that simpler. And then let's scale this, or simplify this, scaled unit tangent. I know it's pretty simple at the moment, but in our program we might want to present them as simplified values. All right. Certainly look how much simpler that becomes. Right? Where if we now plot that, it's going to be plotted similar to P6, but for brevity's sake, I'm going to copy and paste this over and make my changes. All right. First of all, it's going to be called P7. It's going to be the next one in the lineup. It is going to start at RSC, and we're going to add to it the scaled unit norm. I won't miss my U that time. At C, and we're going to make that full scale. Plot style directive, and we got all that. And then we come down here and make this P7. All right. And you can see there it scales it out, folks. All right. This vector plus this vector yields this vector seen here. All right. What we could note there, for instance, what I am saying there is if I take the scaled unit tangent vector with respect to t, and I add that to the scaled unit normal with respect to t. Right? That does give me this down here. Let's simplify that. All right. It simplifies to this description 0, 2. 0, 2 should look familiar. That is your description of acceleration, folks. All right. That is your acceleration. Your acceleration is a summary of this vector scaled with this vector, or added to this vector. All right. That's a summary of that, quite literally, a summary, right, of those two vectors scaled. So it's this vector added to this vector will give you your acceleration vector seen here, folks. And we can adjust that along here with our value of c. We're looking at it at 1/2. Maybe we look at it at 2. And you can see it out here, right? How things change. Certainly, what we're illustrating here is our acceleration, because more of that summary is happening in the tangential direction than in the normal. Right? Notice the dotted line only goes into the pink about halfway, the magenta about halfway. Right? And whereas this vector is certainly much longer, right? Due to the angle of this acceleration vector relative to the forward motion, right? this is showing us that much more of the acceleration here is due to a change in speed than what is due to a change in the direction being in this direction of the unit. Normal vector, folks. All right. This is a mighty long program, and it did take me a little while to get through that. Very buggy at times. Some of it my fault. Some of the errors, things you got to watch out for as you're programming, folks. But a lot was built into this, and you can see the depth that a program can start to develop. And I did a little bit of documentation in here, but I'm going to leave it as is because we are at the hour. To make it go three-dimensional, you would have to go through like we did in the previous cases and change all your plots to three-dimensional plots. But where you're also going to hit an issue is right here. You actually won't need these velocity 3D declarations, and you would be able to just go back to a regular velocity and acceleration in this cross product. All right. Otherwise, everything else, all your plots you would call out as parametric plot 3Ds, and your list plot would turn into a list point plot 3D. All right, much like we saw in the other demo, folks. But you can see I like programming. I like programming in Mathematica. Notice what we did here. We did, we built this little program, and it tells us quite a bit. All right, quite a bit here. We might say this is what did we build here at the end? This is our verification of the acceleration summary. Right. But what we built was this item that tells us not only the velocity vector, but will tell us at a specific chosen value. And it'll also do that with the, we'll get the components of acceleration if we actually wanted to call those out at our specific value. Right. We could take that tangential component and consider its value at C. And we could actually print that. And it is printing that. We could take that a step further, though. Copy that. And add the line at t equal to, and then outside here put C, following in a comma. And then we will do that with this one. We declare it here. So let's print it here. At t equal to, comma, C. And then we'll do the acceleration normal at C. And that tells us the normal component of acceleration at t equal to 2. Or we could talk about the tangential component of acceleration at t equal to 2. Right, they're two values respectively. Right. But folks, yeah, this is a nice little program that I've put together for you here. But at the moment, like I said, we're over an hour. I'm tired. I'm going to close down for the night. Again, putting this all together for you. I think we did curvature in class. I did a program, and I posted that up last week for curvature, and that covers quite a bit. We could play around with arc length in here if we wanted to. Maybe we'll do that, but really what these are ones where we might need some help visualization with that visualization aspect. We could go a lot further in these demos, but like I said, we're an hour in, and we already have something here. I certainly could take it further into curvature, but I will leave it at that. I got a terrible spelling. Even when it tells you it's wrong, I can't see it. All right, folks. With that said, I will end there and see you Wednesday in class.